Right, SPC5 isn't anything too strenuous. We're just going to have a look at power and efficiency. So we'll introduce this equation here, P equals VI, and a couple of variations on that. And so we're going to have a look at how we can measure the total power when we're looking at circuits. So we've spoken about the voltage that's across some component, we've spoken about the current that's passing through that component, and finally we're going to formally look at how do these voltage and current combine to tell us what's the actual power being delivered to this component or being dissipated by this component. So next lesson we'll have a look at the photovoltaic effect, which tells us how solar cells manage to turn light energy into electrical energy. And so energy is transferred, and let's see if we can work out how we get to this equation. So power is measured in watts, which is joules per second. Voltage is the number of joules per coulomb, so work done per unit charge. Current is charge per unit time, so that's coulombs per second. And so we can see if we want joules per second, if we do joules per coulomb from the volts multiplied by coulombs per second from the current, then these two coulombs will cancel out and we will be left with joules per second. So we can see that power is quite simply voltage times current, a lovely straightforward equation. But we also have Ohm's law. So V equals IR, which we can also rearrange for I as I equals V over R. And so we can take each of these and substitute these into here. So if we substitute this first form into here, instead of V we're going to have IR. And so we'll get I squared R. Up here, if instead of the I we stick a VR, we're going to have V times V over R, which gives us V squared over R. So if we know any two of voltage, current and resistance, we can work out the power. And so let's have ourselves a brief circuit so that we can talk about this. So if we've got, let's get the pen back, if we've got our cell and it's connected up to a load with some resistance, and we measure the current, and we also measure the voltage. What we're talking about is the power dissipated by this supply is given by P equals VI. So if we measure this voltage and this current, we can work out what's the power being dissipated in here. So in a resistor, that's going to be dissipated as heat energy. In a bulb or an LED, that's going to be dissipated as light energy plus any other resistances, or some other useful energy. In a motor, we're turning it into kinetic energy, for example. But we also had the other two forms, P equals V squared over R. So if we knew the resistance of this component and the voltage across it, but we didn't know the current, we could use this to work out what's the total power output by this. And our other form, P equals I squared R. Again, if we knew the current and the resistance, but we didn't know the voltage this time, we could still work out the power dissipation by this component. So just a couple of straightforward equations there. And if we're talking about solar cells again, let's have a look at efficiency. So the efficiency of a solar cell turning light into electricity varies from about 10 to 40% depending on the technology that you're using. Most of them are around 20% at time of print, and who knows what the future holds. And so efficiency we know to be the useful power out over the total power in, or the useful energy out over the power useful total energy in. We can actually draw a couple of comparisons to our last lesson where we were looking at internal resistance. So we said that the total voltage being output by a cell is its EMF E. Whereas what actually gets out to the resistor or to the external circuit is the terminal potential difference, so the uppercase V. And so if we've got some current passing through a circuit, the total power which the cell is putting out is epsilon I, and the useful power which is actually getting to our load is VI. And so we can take the ratio of these and work out what the efficiency is. And this is going to vary depending on what the current is. So the efficiency is going to vary on with the current, because remember we saw our equation was V equals epsilon minus I R. So these are our lost volts. These are how many volts are lost. And so if we're looking at our efficiency, basically boils down to our terminal PD over our EMF. And so as our current increases, this is going to decrease for the same EMF. And so as the current increases, our efficiency is going to go down. For a small current, we're going to have high efficiency. But as the current changes, we're also going to change the current that's coming out because of this equation. And so in the lesson, what you'll do is you'll perform a little experiment. You'll get Excel to do some number crunching for you, and we'll come to some interesting conclusions. So these are our equations, and the conclusions you'll hopefully reach in the lesson are something which we know as impedance matching. So actually it turns out that if you want to draw the maximum amount of power possible from the supply, so we're not talking about the efficiency, we saw that to get the maximum efficiency, what we'd have to do is have as large an external load as possible so that our current is as low as possible, so these lost volts are as low as possible, so our EMF is as close to our terminal PD as possible. So that's our efficiency. For maximum efficiency, we want a low current. But if we want to get the maximum power out of a supply, you'll see that actually we need to match the impedances or match the resistances such that the resistance of our load is exactly equal to the internal resistance of our power supply, which is an interesting concept. It's known as impedance matching. Is used quite commonly in acoustics. So when you have your amplifier and you hook it up to your speakers, you need to impedance match your amplifier with your speakers. So your speakers will have a resistance on them, listed on them somewhere, and so will the amplifier. And in order to get the most amount of power possible to these speakers, you need to pick a pair of speakers which have got the same resistance as your amplifier, which is effectively your power supply in this scenario. And so in the case of the satellites that we're contextualizing this all in, if we're only able to get a limited amount of power from our solar cells, then this tells us that we need to arrange our solar cells and our load in a manner such that if we want to get as much power as possible, we don't really care about the efficiency with solar cells because we can just allow more light to come in. If we want to get the most power that we can, we need to match the load resistance against the internal resistance in order to do that. So that's all for this lesson.